LSD stands for lysergic acid diethylamide, and it's one of the most famous of illegal drugs. It was actually discovered back in 1943 by a Swiss pharmaceutical chemist called Albert Hofmann, and he discovered that it had a potent effect on the central nervous system, again by accident. LSD is a semi-synthetic. It's a semi-synthetic derivative of alkaloids found in Rivea corymbosa. It had great popularity back in the 1960s. Now it's relatively uncommon. Probably the main reason for it being uncommon is that other semi-synthetics are much easier to make than LSD. It's a potent hallucinogen, and it works by disrupting communication between the neurons. LSD itself probably never killed anyone, but there have been numerous fatalities arising due to LSD usage. The reason for these fatalities is that some people, after taking LSD, believe they have the ability to fly, which of course they don't. Nowadays, probably the major threat from semi-synthetic drugs is from the amphetamines. As you can see, they're much simpler structures than LSD, and therefore they're much easier to make in backwoods illegal laboratories. There are various recipes for how to make different amphetamines that are available, and forensic scientists can work out which method was used for a particular sample of amphetamines by looking at the characteristic impurities that are left over from the synthetic route. Let's consider the synthetic drugs, those that are made by chemical means. Now imagine you're the head of the drug squad in a city or a county, and your officers have collected samples of synthetic drugs through various raids and arrests. And you probably want to know whether these drugs are all coming from the same single source, or whether they're coming from multiple sources. This would be a useful piece of information. How can you find out using forensic science? Well, let's consider the synthesis of drugs. Drugs are synthesized by chemical transformations starting from simpler molecules that can be acquired commercially, either purchased or stolen. Now, these chemical transformations, typically you can't take your commercial material and in a single operation convert it into the drug that you want to make. Sometimes that's possible, but often it's a multi-step procedure going through synthetic intermediates. You buy the chemical, you convert it to an intermediate, and then you convert it onwards, maybe through other intermediates, until you get to the drug that you want to make. Now, this kind of chemistry is not only done by people in the backwoods in clandestine chemical labs, it's also done by the pharmaceutical industry. So both the illegal drugs on the street and the legal drugs that you get from the pharmacy are produced by synthetic organic chemistry. Of course, there are big differences. Obviously, the pharmaceutical industry is legal and the clandestine laboratories are illegal. In the pharmaceutical industry, the synthesis of drugs is very, very heavily regulated. In the United States, this regulation is carried out by the Food and Drug Administration, the FDA. And the long arm of the FDA will even reach out to manufacturers outside the US and punish them for transgressions. So the process chemists, that is the people who make the drugs in the pharmaceutical industry, have an obsession with purity. They have to make sure that their products are as pure as they possibly can be. Obviously, the clandestine drug labs, they are not regulated at all. Do they do any type of quality control on their product? Unlikely. And this is how we can find out whether drug samples come from the same source. It's not by looking at the drug molecule itself, but it's looking at all of the impurities that are present. And these impurities can give us information about how that drug came about. We will take one example, and that is methamphetamine. There are two routes by which methamphetamine is made clandestinely. Actually, with synthetic organic chemistry, there are dozens of ways that you could make methamphetamine, but these are the two that are used. One starts from a chemical called ephedrine, and this can be bought or acquired in large quantities because it's used in a lot of very simple medicines. For instance, it's used as a decongestant. The other starting material that is used for methamphetamine is an industrial chemical called phenyl 2-propanone. So we have two different starting materials for methamphetamine. So while we have two different starting materials, from ephedrine we actually have 5 different chemical methods for converting it to methamphetamine. And if you compare the structure of ephedrine and methamphetamine, you can see that the only difference is the presence of an oxygen atom shown in red. So this chemistry is simply to remove that oxygen atom from the molecule. So 4 of the methods that are used are direct removal of the oxygen atom. And you can see that 3 of them are quite closely related because they use phosphorus chemistry, the Nagai, the Moscow, and the Hypo methods. And then there's a 4th method, the Birch method, which uses lithium and ammonia. If we take the Nagai method as an example, then what are the characteristic impurities present in methamphetamine using the Nagai method? This is one of them, and it is characteristic of the Nagai or maybe the Moscow methods because it incorporates an iodine atom. It's methamphetamine with an iodine atom attached. And because the Nagai and Moscow methods are the only methods that use iodine, the presence of this impurity indicates that this chemistry was used and that ephedrine was the starting material. On the other hand, the Birch method will produce this as an impurity. And anyone who knows some organic chemistry will know immediately that this kind of molecule can only be produced by Birch chemistry. None of the other methods can produce this compound. It's absolutely characteristic of the Birch chemistry. There's also an indirect route for converting ephedrine to methamphetamine, and this is the MD route, which involves first conversion of that oxygen substituent to a chlorine, and then removal of that chlorine using hydrogen gas and a catalyst. So the characteristic impurity for methamphetamine produced by this route is the presence of that chlorinated compound. And what this indicates is that the chemists doing the transformation of the chloro compound to methamphetamine didn't follow the procedure correctly, and they stopped the procedure before the reaction was complete. And therefore there's a little bit of leftover chloro compound in their methamphetamine. So if you detect that chloro compound in the methamphetamine, then it indicates very strongly that those chemists were using the MD route. Now, we know that methamphetamine can also be produced from phenyl 2-propanone. And one method for this transformation is called reductive amination. It involves treating the phenyl 2-propanone with methylamine in the presence of aluminium and mercury chloride, which is a pretty toxic mixture. What kind of impurities would be characteristic of people using this route? The answer is this phenyl propanol, and in this case the oxygen atom is still there, the nitrogen hasn't been introduced. So it's where some of the molecules have done the wrong thing and have not incorporated the nitrogen atom. Another impurity that is reported to be characteristic is this compound here. It's methamphetamine, but there's a carbon atom missing from the nitrogen. And this probably arises from the use of impure methylamine. So if the methylamine that they have acquired contains ammonia as an impurity, then this compound is produced. This would not happen in the heavily regulated pharma industry, because in the pharmaceutical industry, before a chemical is used in the process, the purity of that chemical is checked. This is not going to happen in clandestine drug labs. There is an alternative two-step procedure to the reductive amination, and this is the Leuchart method, in which the phenyl 2-propanone is first reacted with a chemical called N-methylformamide to give an intermediate, and then that intermediate is treated with hydrochloric acid, and that cleaves off that oxygen-containing substituent on the nitrogen atom and gives the methamphetamine. A characteristic impurity in this case would be, again, that intermediate. So if that acid treatment wasn't done properly, then some of the intermediate would still exist and it would be detectable in the methamphetamine. Another impurity that is reported to be characteristic of this route is this compound on the right. And again, this arises from impurities in the starting material. If the starting phenyl 2-propanone is impure, then this is likely to be produced. So we have taken methamphetamine as an example. The same exercise can be carried out for all the other amphetamines. Each amphetamine has its own routes, some related to the methamphetamine routes that I've shown you. And again, there will be characteristic impurities for each of the individual different amphetamines. And by looking at these impurities, forensic scientists can tell which routes were used. And different clandestine laboratories may well use different routes. And so you can get some idea of how many different labs are out there supplying these amphetamines onto the black market. That's the chemistry. How is this actually done in practice? Forensic scientists would use the techniques that we talked about in an earlier lecture to detect these impurities. They would use the chromatographic techniques and spectroscopic techniques such as GC, HPLC, mass spec, IR, and also other techniques that we haven't had time to talk about to detect and identify and quantify these molecules. So once again, this is an example of Leuchart's principle that every contact leaves a trace. But in this case, the trace is not telling you who committed the crime, but it's telling you the method, how they committed the crime. One way to control the amphetamine business, of course, is to hunt out the laboratories and shut them down. That's not easy, and many countries nowadays operate what is called precursor control. There are certain starting materials that are used in these routes to make amphetamines, and the authorities watch to see who is buying these starting materials. And if those people can't give a good reason for buying those chemicals, then they may be in some trouble. Now, the amphetamines do have some natural relatives. For instance, this compound here is called cathinone. And the cathinone is present in the leaves of this plant, which is called cat. And this is widely chewed in the Horn of Africa and the Middle East, particularly Yemen. It's a particular problem for this part of the world because to grow this plant, a lot of water is required, and none of these countries have very much water. It's chewed fresh, and that is because cathinone, the active ingredient, is not very stable. So if you dry the plant, for instance, you'll lose that active ingredient. Cat is illegal in a number of countries. For instance, it's illegal in the United States of America. So people from this part of the world, if they're traveling to the United States, can't take the material with them. Ketamine is quite different to the compounds we've talked to so far because it is a purely synthetic compound. It was introduced some years ago as an anesthetic. Ketamine is still used in human medicine, but treatment for the other effects of the drug is necessary. For instance, there was one little boy who was given ketamine as an anesthetic before an operation, who then hallucinated for the next 3 days. Ketamine is also used in veterinary medicine. Whether or not animals can hallucinate, we really don't know. Ketamine gets onto the illegal drugs market, mainly when it's stolen from veterinary supply companies or veterinarians. It's a hallucinogen. It also affects memory, it affects sensation, it affects mood, it causes delirium, it causes amnesia and depression. The fact that it causes amnesia means that it's been used in cases of date rape. Ketamine may be in a solid form, it may be in a liquid form, it may be ingested, it may be smoked, it may be injected, and whichever way, it's a dangerous material.